Okay, picking up with piston displacement, because the last video that you should have watched was on the compression ratio. And so we worked out our compression ratio, what was going on there. And so again, piston displacement, just to review it, depending on how long ago it was you watched the last video, piston displacement is with that piston down at bottom center. And then, of course, we travel up our full stroke to where we're at top center. And so that amount of area that we call is displaced by the piston, that's what we're going to be figuring up our cubic inch size of the engine. So in the last video we discussed I have to have certain given information, and that's where we have to know what our bore is, and we have to know what our stroke is, and what our number of cylinders are. Of course, that's the easy one, especially on a little Lycoming, what you're going to be working on, the 4-cylinder engine. But the basic formula that I use, make sure I get some weird glare on the thing there. The basic formula that I use in this is our pi r squared times the height times the number of cylinders. Okay. So you can look up, you can measure the cylinder. As we mentioned, if you had a choke barrel, you want to be down towards the bottom, within a couple inches, 3-4 inches of the bottom, and which you guys will be learning how to measure those with your telescoping gauge and micrometer calipers. And one problem we've been having as you do your oral and practicals is that basic bore size, for some reason, is not in the Lycoming table of limits. So if the examiner sets a Lycoming cylinder in front of you and wants you to measure that guy up, and you go look at your table of limits, so that's why I want you to kind of write down a secret place or somewhere that the basic bore size, a standard barrel, 5.125, 5 1/8 inch is the size of that barrel. Because they tend to give you just maximum limits that you can work with. Okay, so in order to plug the numbers into this formula here, we've got pi, which I use 3.1416, and then they want radius squared. So the radius of 5.125 works out to be 2.5625. So times times 2.5625, then square it, meaning multiply it by itself, 2.5625, times the stroke, which is 3.875, and of course times 4, number of cylinders. And if you get a chance when you kind of get away from this video to practice this, it'll actually come out to 319.74. Hope that came in on the screen over there. 319.74. So what they do when establishing the, where this is an 03, these are the numbers for an 0320, they always round off to the nearest 5 number. So since this is 319, they call it an 0320. If an engine's came out to something like 326, they would call it an 0325, whatever the nearest 5 number is for calculating that up. Okay, then we're going to take a look at what happens if we oversize the cylinder. So that term boring a cylinder, where you increase, where it's put in a great big machine and has a cylinder spinning one way and a stone that's traversing in and out of the cylinder going oversize on that cylinder, versus honing of a cylinder. A hone is what you're going to be learning to work with too here. Is this is a rigid hone for going in and working on that cylinder wall to establish the cross hatching in the cylinder. There's also other types of hones out there. This one's a deglazing hone that goes in and takes glazing off the cylinder. It can also smooth up if you were a little bit rough with your other hone. Out in the industry, these things are also referred to as a goat turd hone, because if you've ever been on the farm, whatever, goat turds are these little round, poopy balls. And so, anyway, it's a goat turd, but actually the professional name is the deglazing hone. When honing a cylinder, the preferred one because of you get your ring steps and gouges up at the top, and or any irregularities in the barrel. This just follows the old mountains and valleys in the cylinder, whereas that rigid hone will go in and cut that up, to a couple thousandths. That's just for honing. Now let me take you over here for just a second. And when we talk about honing a cylinder, why we're honing a cylinder for two purposes. So in the cylinder here, your cylinder wall, you might have gotten a ring step up here at the top where it's worn out some. It might have where it's gotten a little wide down here and things like that. And you can kind of tell that too when you get your hands of Mr. Goodwrench, and you're doing an inspection on your cylinder where you run your fingers in there and feel that barrel. And so you can tell a lot by looking in the cylinder and taking a look at the hone marks that you see in there, whether they're still there or not. And then you can, as I say, you can run your hands up and down in that barrel so you can feel any of those ridges and problems that might be going on inside the cylinder. But we do hone a cylinder for two purposes. And we talk about that scratching that we do. When I hone that stone in there, I'm cutting little valleys and little mountains get created inside here. And of course, this is going to need to happen until I get this all the way out where that low spot was in there, so the barrel's nice and straight again. But I'm putting these little valleys and mountains on here for two purposes. One is for ring break-in. So as the rings travel up and down the barrel, they're going to get perfectly seated into that cylinder wall, wearing on these little mountains in here. And so it's a 50 micron scratch that we're putting on this barrel that for that purpose of ring seating. After the rings have seated in and the little mountains are basically worn down, then we're left with the valleys. And the valleys there provide for oil retention. And because you've heard that where you don't want metal parts in an engine, metal to metal contact, so we have that film of oil, and it's those little valleys there that help that oil to retain to that cylinder wall. Okay, so coming back over here. So on Lycoming engines, in some cases they can either bore them oversized a certain amount, or in some cases not. Especially when you have a nitrided barrel, the one that has the blue indicator on it that we talked about the other day. Nitrided barrels, they don't want you to bore oversized. But let's see what happens if I were to bore this thing 20 thousandths over. So my basic bore size I would be doing on this thing is I would be adding in 0.20. So the new size of the bore is 5.145. So on your own, you can take and run some numbers out, because there's a new radius here. So you got your pi times whatever that new radius is that comes from the 5.145 barrel size, times still the stroke doesn't change, and of course cylinder numbers don't change. And you'll see it comes out to something like a 322 something. So it still is an 0320. So by boring the cylinder 20 thousandths over, of course, and that's when you've had a lot of damage, when honing can't correct the problem and the cylinder has to be bored oversized, or you got to replace the cylinders, and because they can only bore up to a certain size. In fact, there's a test question that talks about where in automotive industry you can bore 120 thousandths over, 80 thousandths over, and a lot of that also, how much you do depends on what kind of pistons can you buy. But on aircraft cylinders, FAA test question, what's really limiting, or how much, why can't we bore more than, so like I said, with the cylinder painted blue, the like where they paint blue on the fins there of that Lycoming cylinder is nitrided, because it's nitrided. And I'll describe what nitriding's about later. But why we can't bore oversize too much is and the answer to the test question is due to the relatively thin walls that we're starting out with on the cylinder barrel to start with. And And a lot of that, we don't make these things too heavy because remember, these aircraft engines are all about saving weight. We're going to see that demonstrated in many places in the engine where they try to cut down on that weight, because aircraft flying is all about saving weight. In fact, that Lycoming engine we've been looking at over there, that one's weight is right around 245 pounds. So you take the whole thing with all the accessories and everything on it, right about 245 pounds on that thing. And if they could, they'd lighten it up even more, because that's all about. We see the same thing happening within the automotive industry now, where the lighter we can get these, i.e., Ford trucks being made of aluminum now. So because the lighter you can get these things, the less power and the less fuel we burn, better fuel economy. Okay, we'll wrap that up.